MOS transistor second order effects, length and width of the channel, channel length modulation, so it's body effect. Fourth is sub-threshold effect. Length and width of the channel. Due to limitation in the technology, we cannot form perfect rectangular source and drain regions. That is, this cannot be the source and drain regions cannot be a perfect rectangle. It cannot be like this. There will be under diffusion. So there will be some part of drain and source regions which are under the gate. So all this time we were considering the length of the channel to be from this edge to this edge. However, due to under diffusion, the effective length is reduced. So the effective length L equals to L drawn minus 2 times delta L. So this reduction in length is taken care in the software tools like Cadence. Also, the width of the channel is also reduced due to a reason, and the W drawn will be, if this is W drawn, W effective will be smaller than W drawn by 2 times WL delta W. Next is channel length modulation. We know during saturation region, the gate to drain voltage is lesser than the threshold voltage. If this is the gate, and this is source, and this is drain. So in saturation, the drain to source voltage is greater than the gate to source voltage minus threshold voltage. Gate to source voltage is greater than threshold voltage. So if we solve this equation, we find that the gate to drain voltage is lesser than the threshold voltage. So near the drain we do not find channel formed, which is shown here. So the effective length of the channel is L dash and not L. So the length of the channel equals to L minus delta L. So this has to be taken care in our equation, and once we substitute L by L minus delta L, we perform Taylor's approximation, we get this equation: ID equals to beta by 2 UGS minus threshold voltage square into 1 plus lambda UDS. So now the drain current is dependent on the drain to source voltage, and the dependency depends on the term lambda. Because of channel length modulation, the output transfer characteristics curve changes. Without channel length modulation, in saturation region, the drain current is constant and it is not a function of UDS. So this is the constant line according to the old equation. According to the new equation, we see a small slope. So this is the difference. And we also add the term 1 plus lambda UDS in the linear region in order to avoid the step which is seen here. So this is the linear region. Generally in the linear region, 1 plus lambda UDS is not required, but it is added just to avoid the jump in the plot which is seen here. So this jump is not good, and to avoid this jump we use the 1 plus lambda UDS term in the linear region as well. Because of the discontinuity, the simulator will have problems because of the jump. And lambda is a function of UGS, that is the gate to source voltage. It is directly proportional. The lambda value increases with the increase in gate to source voltage, which can be also seen in this waveform, which can be seen in this plot. So if you see, the slope is small over here and the slope increases. So as UGS increases, the lambda value increases. Lambda is also function of length. So as the length increases, lambda is small, and as the length decreases, becomes very small, the lambda value is high. So lambda is dependent on a very good current source. We generally use long channel transistors, channel length transistors. The reason is we want the lambda to be small, so that for changes in UDS the current remains more or less constant. So we use long channel length transistors, so that the lambda value is very small, that is the slope is very small. Second effect is the body effect. When the bulk and source are shorted, we do not see the body effect because U source to bulk voltage is 0. However, in a single well process, in some cases, in such a circuit, the bulks of the MOS transistors are same, and hence if the bulk is connected to VSS, the upper transistor bulk is also connected to VSS, and because of this we have VSB, that is source to bulk voltage, and this results in body effect. So because of the body effect, the threshold voltage UT equals to UT naught plus gamma times square root of 2 phi f plus USB minus square root of 2 phi f. Because of USB not equal to 0, the threshold voltage is UT naught plus this term, so UT will be greater than UT naught. Here gamma is called as body effect coefficient. No need of remembering this equation. However, just remember that gamma depends on the doping concentration of the substrate, that is defined by the technology, and phi f is the Fermi potential. It again depends on Ni, that is the intrinsic charge carrier concentration in the substrate. How do we avoid body effect? We can avoid body effect by using a triple well process, where each NMOS transistor as well as PMOS transistor has a separate bulk contact, and we can short the source and the bulks. However, the triple well process requires more area and hence more money. The last second order effect is the sub-threshold current. Our assumption was when the gate to source voltage is lesser than the threshold voltage, and when UDS is greater than 0, the drain current should be 0. However, this is not true. There will be a very small drain current flowing, that is the leakage current, and it depends on this equation ID. It is a function of temperature, that is UT. UGS, it also depends on the UGS value, also depends on the UDS value. You can see the graph over here. This is the threshold voltage of 400 millivolts. So when the gate to source voltage is lesser than 400 millivolts, we expected the drain current to be 0. However, in the sub-threshold region we have currents in the range of 1 micro to 10 nano amperes, which is so. In order to reduce the leakage current, we have to reduce the gate to source voltage,